Bismillah ar-Rahman ar-Rahim. I really impressed to be here after 11 years of establishing the ACI chapter in Iraq. The first time when I came here to meet my friend Dr. Omar Qarani and put this idea on the table and say to him, please go on and start the ACI activities in Iraq, and really see now this event happened. And maybe this is the first time we receive a delegation from ACI, Dr. Khalid and Mr. Ahmed Limhanna. So thank you for Kurdistan chapter and the organizers. I will talk about a code. It's not well known like the ACI 318. It is the 350. Why we need such code, especially in Iraq, when building our infrastructure facilities. Maybe most of you are engineers and dealing with concrete as the designers or constructors and so on. Always there is a concern, which is cracks. Cracks is important to be controlled for designer to satisfy two requirements. They are the serviceability requirements and durability requirements. And this is for ordinary building. But for environmental engineering concrete structures, the function will be how to keep the liquids and water, etc., inside those type of structures. So the cracks will be effective for the function. But let me define first what the meaning of environmental engineering concrete structures. I will use the section of 111 from 350-20. It is those facilities used for conveying, storing, treating the water, wastewater, or other liquids, and so on. So one of the examples is this treatment plant, which is constructed recently in Karbala, and I think there's a lot of such facilities in Kurdistan region. So let me return back to the history and our traditions, because I have also interest in the cultural heritage. So can we get rid of the tension? Because the cracking always is caused by tension. There are a lot of attempts how to get rid of, have structures without tensions. One of them, this is Swiss structural designers, passed away at 2009, started to invent such type of non-tension structures. And we returned back to the history and found that the first sketches of Isler is maybe it's inspired from the Ctesiphon in the middle of Iraq and the large catenary shell, which is maybe the largest catenary shell in the world, and the same shape with a minimum potential of energy, as you know. So ACI started to deal with such type of the structures or concrete structures, but the name at the beginning is sanitary engineering structures. And the first reports was published, the first one as 1971, after many years of work. The main idea how to control the cracks, because we cannot have no tension structures, so the cracks is always exist. But the alternative way is to control the crack, which means limiting the width of cracks. The well-known equation of crack width, which is Gergely-Lutz, used by ACI 318 in 1971, was adopted in this report, and you can see it is a direct relation between the W, which means the crack width, and the steel stress. Because as you know, we bring the steel to resist the tensile stresses inside concrete structures. And the working stress method was used by the report because maybe it is the first time in the ACI 318 to use the strength design, so it is not adopted by this report. Later, the report, before talking about the other report, it's 1989, but later at 77, this equation of Gergely-Lutz was adopted by the ACI 350, and we will compare what is the difference between the crack control in ordinary concrete structures and, I can say, sanitary concrete structures. So if we now take the ACI 318 of 1971, we have two exposures in crack control, which is interior or exterior, and then we have the Z factor, not directly dealing with the width of the crack with the W parameter. So for the interior, the limited value is 175, and for the exterior is 145, which means if you want to feel the crack width, if we measure it by crackometer, it is that the maximum crack width allowed is 0.4 millimeter only, and for interior, like column and beam in the interior of the space, and for the exterior structural members, it will be 0.33. But related to the sanitary engineering structures, the thing is different, because the exposure is not interior and exterior. It's not as simple as that. It is normal and severe. And the measure, or the way to measure what's the difference between normal and severe exposure, it is related to the percentage or the concentration of the sulfate inside the material which is contained in such structures. For example, the sewage or the water, raw water, and so on. Or use this pH parameter to see how it's the alkali material or not. So let us compare the values. We will see that the crack width is limited to 0.25 in normal exposure, and it's only 0.2 millimeter in severe exposure. Let us now imagine what will be the steel stress, because I say in the beginning, we cannot avoid tensile stresses. So let us limit it, these stresses. As you know, the tensile stress will be carried by the steel only. So the steel stress will be here 0.6 Fy, but for the sanitary engineering structures, it will be limited to 0.3 to 0.45, and depending on the type of exposure. Later, another report was published at 1983, and it is time to adopt the strength design method, because maybe we have 10 or more than 10 years that the ACI 318 adopted such philosophy in the design. And this is the main equation of the strength design method. And if you now think how this report be familiar with the same philosophy, how to control the stresses or the tensile stresses inside the structures and then limit the crack width. So they used to equalize the two forces, which is calculated by ultimate and the service load or the allowable stress method. Let us explain this in an easy way. I consider this circular tank, and as you know that the main dominating in the design here will be the hoop stress, T. So if we use the ultimate strength method or the strength, it will be the equation like that. And if we use the allowable stress method and equalize both of those forces, we will find that this equation. So now let us consider one of the exposures, and then the crack width limited to 0.2 millimeter in severe exposure. And then we will see that the both equations are not equal. We need another parameter to equalize those equations. This parameter named sanitary durability factor at that time, of course. So in other words, we can say that we should increase the loads more to have less stresses, and then less crack widths. This is the main idea. And this report at that time used a constant value for this durability factor. And for example, for hoop tension or direct tension, it was 1.65. So later, for a flexure, the same idea, but another equations. I have no time to say it. But at the report published in 1989, this factor changed the name from sanitary durability factor to environmental durability factor. This is because that the whole report title was changed from sanitary engineering concrete structures to environmental engineering concrete structures. And as you see, it is clear that the constant value for this factor was adopted at that time, because this idea was developed in another way. The first code in this millennium, the new millennium, was published at 2001 with the name or with the number ACI 350. And later, there is a code at 2006, but the main idea between, or the common idea between them, that the durability factor, it was calculated by equation, not constant values, and this equation, there are many parameters, like phi and f sub y and so on, but the main parameter I can say it is the maximum steel stress, which will define, don't forget that, the maximum crack width allowed in the design. Constant values are used for hoop tension, but for the fracture, we will see that are values, another way to calculate this. The code published recently at 2020 adopted the same values and the same equation with the same symbol, and for a fracture, you can see that there's a lot of change. It is very, also I can say it is a huge change in adopting the main philosophy of how to control or how to calculate the crack width. In the beginning, as I mentioned, that the code or the report adopted the Gerli-Lutz equation. But when ACI 318 moved to another equation, which was written or published by Frosch, I think at the late of 90s, also the code of ACI 350 followed this idea and this new equation. And I think maybe all the graduated engineers graduated from this, they studied the Z factor, but the new engineers now studying only the maximum spacing in the ACI code, how to calculate maximum spacing between bars to control flexural cracking. However, that the FS max, now they have new equations dependent on the Frosch equation. To show you the difference in engineering sense, we are engineers. We want to deal with numbers, and the output is very important for us. I consider now one example, it's a virtual example. We have a water tank designed as a cantilever with a fixed base. I will use ACI 318 and design this cantilever wall of this tank. The wall thickness will be 400 millimeters, reinforced with 516 millimeters each, spacing at 200 millimeters. But if we think in the durability, in the function, in the water tightness, and so on, so we should use, or we shall use ACI 350, and you will find these results. So to control crack or crack width, you have to increase the wall thickness by 88%, or you have to increase the reinforcement by 60%. So this is the difference between ACI 318 and ACI 350. So I can say, this is my sentence, not of the code, that in the ordinary design, the design controls the crack width. This is familiar, or it's a common sentence. But I can add that the crack width will control the whole design in such type of structures. Recently, 1 month ago, I checked the design of some facilities in pumping station at Nahrawan, a treatment plant at Baghdad. Those facilities was designed, I think, at 2014 using the old ACI 350. But I used the new ACI 350 and to find if the design is good or not, or must be checked. I find this. When I use the new ACI 350, there's a reduction in the reinforcement about 350 tons, which made some problem between the contractor and the client, because there will be such change orders about the price and the contract and so on. But this is a strange thing. Why the reinforcement is reduced in those pumping stations? I will tell you. We have other, up to now, I am talking about one type of cracks, which is the flexural crack. But we have another type of cracks, which is very important. It is the shrinkage and temperature cracks. Yes, it happens at early ages of concrete, but really, it's really bad things for the whole people dealing with concrete, the contractor, the designer, the client, and so on. When, after removing the shoring and the forming, they saw a lot of cracks, crazy cracks, as they mentioned in this. At the beginning, ACI 350, the reports used those ratios as a minimum. We called minimum reinforcement. For simplicity, I will call it minimum reinforcement, no shrinkage and temperature crack. So the maximum is 0.006 and the minimum is 0.003, and the minimum of this table is larger than the minimum in the ordinary walls, which is 0.0025. Later, they are improved in another graph and so on, and in the report added sketches for the contraction joints, because it is important to control the shrinkage crack not only by reinforcement, also by using contraction joints, as you know. Okay? The code, or the last code before the recent code, let me say like that. Now, there are two types of steel reinforcement, grade 40 and grade 60, and you can see that the maximum secondary reinforcement is 0.006, but it depends on the distance between the contraction joints. One of the major changes at the recent code of 350 is that it used another way to control cracking by reinforcement and contraction joints at the same time. There is a new parameter which is restraint. As you know, cracking is happening because of the shrinkage and temperature when there is restraining to the movement. If the movement is not restrained, there are no cracks. So here, the code defined three types of restraining depending on the position of those reinforcement and the position of the stresses. I will show you one of the example. Let us imagine this wall. It is a real photo, and you can see clearly that the cracks from where it begins and then propagate. So the code said that the ratio of reinforcement should be 0.01, which is more larger than the maximum 0.006, as you saw before the previous slides. But where? At this strip, 1.8 meter above the bottom of the wall only, and in the horizontal direction. So this is the most risk region in the wall. But no need to use this ratio for the whole wall and for the two faces. For this, you can, for example, define reduced strain, only 0.0025, which is less than 0.003, the minimum of the last or the previous code. And then you can use normal restraint for the other position of the wall. This is the reason why the amount of reinforcement I found it is reduced by about 350. I don't know the percentage inside the whole project. Also regarding the slab, the reinforcement can be 0.005 or 0.01 dependent on the position. Only the strip which is parallel to the concrete wall, because the concrete wall will be the cause of restraining of the slab or the movement of shrinkage stresses, and so on. And in the new code, there are a new chapter, chapter 7. It is for joints and the details of joints. Also, I want to mention that the durability requirements in such type of structures are very important. How many minutes I have? Oh, yes. Let me be fast. And there are also a new types of exposure in such type of structure. A new types related to the ACI 318, and more restricted also requirements, and also those are the protection against chemical attack. And finally, let me briefly explore the arrangement of this new code and regarding or compared to the old code. You can see that a new chapters was added for this code, and the code in the beginning and still up to date is based on the ACI 318 in the organization, but the old ACI 318, not the new organized ACI 318. So this is ACI 318 11. you will see now the change in the chapter and the organized, and a new chapter which has a formwork and embedment, and the development length and other reinforcement details was moved to chapter 12, and the new chapter about joints, chapter 7. So the details of reinforcement, as I mentioned, was part of chapter 12. The other chapters also, chapter 21, and the earthquake design of such structures, it was chapter 13, moved to chapter 13, and the numbering of the whole chapters was changed because of that, as you see. And also, I think there is a new chapter, which is condition assessment, which added to the chapter 22. I hope this will not compete ACI 562, Dr. Khalid, but it is just simple ideas how to, I can't say repair those facilities, but just how to explore the damages and so on, how to write reports, etc. And the new chapter also regarding this type of structural facilities. And thank you for your listening.